All right, so today we're going to talk about PMOS devices. And we'll wind up going through this pretty quickly because we've laid a pretty strong foundation already, or at least I'm of the opinion that we have. So we already saw the basic structure of a PMOS device when I introduced MOSFETs, right? So we would have an N-type substrate and then a P+ implant serving as our source or drain, and a P+ implant serving as our source or drain. I'm going to put my body implant up here. So we have our drain terminal is at the lowest electric potential. Our source terminal is at the highest electric potential. And then we typically bias our body or our bulk to be at the highest electric potential as well, which is why I'm putting the body terminal on that particular side. Then we have our oxide layer, on top of which we and here is our gate terminal. So just to be really clear here, for a PMOS, source is at highest potential. Drain is at lowest potential. And our drain current flows from the source to the drain. All right, so we're not going to go. Somebody isn't muted, so I'm hearing myself and it's distracting a bunch. Daniel, you're on the front row and you're not muted. Oh, well then, I don't know. Yeah. All right. So we're not going to go through a full derivation of threshold voltage and all of that kind of stuff because effectively it's the exact same process, except now we're pulling minority carrier holes into this region to form our channel, and effectively everything else works literally the exact same way, right? So we can define our cutoff region to be whenever our source gate voltage, VSG, is less than or equal to the absolute value of our threshold voltage for our PMOS device, which is what VTHP stands for. Now, I think I've mentioned this a couple of times, but for whatever reason, the threshold voltage of a PMOS device is always given as a negative number. If you throw the negative sign away, you don't have to worry about the absolute values. Technically speaking, I'm going to do everything formally here, like you'll see in the textbooks, but technically speaking, if you throw the negative sign away on the threshold voltage for the PMOS device, and then just swap every subscript, you will get the exact same relationships. The only thing that's going to be very slightly different is one of the quantities in our full resistor bias network, and we'll get to that in a moment. Okay. So in cutoff, our source gate voltage is less than our threshold voltage, meaning that we have not hit strong inversion, and we're going to say that current can't flow through the device, right? For our triode region of operation, we need our source gate voltage to be greater than or equal to our threshold voltage. And we need our source drain voltage to be less than VSG minus the absolute value of VTHP. And under these conditions, our drain current ID becomes mu P Cox W over L VSG minus the absolute value of VTHP times VSD minus 1/2 VSD squared, or K sub P times VSG minus the absolute value of VTHP times VSD minus 1/2 of VSD squared. So incredibly similar to what our triode relationships look like for an NMOS device, except that our subscripts have changed from GS to SG, from DS to SD. We're using an absolute value sign to take into account that our threshold voltage is arbitrarily negative. And we have a KP instead of a KN because we're using the P channel mobility as opposed to the electron. So we're using whole mobility as opposed to electron mobility for our majority charge carriers, right? For saturation, we have the constraint that our source gate voltage needs to be greater than or equal to the absolute value of our threshold voltage. And now our source drain voltage needs to be greater than or equal to VSG minus VTHP. So same as the basic conditions for saturation outlet. NMOS, just swap the subscripts around. And our drain current will be ID is equal to 1/2, sorry, I missed the 1/2. Mu P Cox W over L times VSG minus the absolute value of VTHP squared. And then I'm going to do this part in blue because it's optional, times 1 plus lambda VSD if channel length modulation effects are included. In terms of our generic transconductance parameter Kp, this is going to look like 1/2 Kp times VSG minus the absolute value of VTHP squared. And once again, optionally, 1 plus lambda VSD, whenever we choose to include the effects of channel. All right, so those are the basics relationships for a PMOS transistor. So now let's go through our bias circuits and we'll be done. I'm gonna eat this piece of candy, yes.
So would these equations be on a phone?
Absolutely, yes. I don't remember, I explicitly remember asking you guys to shoot me an email to remind me to look for the equation sheet. I don't remember receiving said email, so I forgot about it until just now when you asked. So once again, knowing how utterly forgetful I am, if you want to make sure there's an equation sheet, send me an email to ask, hey, where's the equation sheet? Yeah, doing it right now is a great idea. All right.
Speaking of emails,
Oh,
I don't think you got the one you said.
Yeah.
that's, I sent it as an announcement on Canvas. Let's pull that up really quickly.
Okay.
So if I go to my dashboard and I go to 335, I may have misremembered this. Announcements. Oh. What class did I email about? Okay, well, apparently I either emailed the wrong class and they're like, what the hell is going on? Or I forgot to hit send or whatever. Okay, so sorry about that. I guess I'll tell you explicitly now. I could have sworn I sent an announcement. I really don't know what class I sent it to. I decided to put the exam, keep it on Wednesday, A, because some students preferred it to be on Wednesday and it was already scheduled for Wednesday to begin with. And B, so that you could have your grades for the take-home portion of that exam available to you before the drop date. Okay, so it is what it is. I said if any single student had a comment about it, I would keep it on Wednesday. There was more than a single student that requested to keep it on Wednesday. And it was already on the schedule for Wednesday to begin with, so. I will officially send out an email about that to the correct people sometime today. All right, so 4 resistor biasing network. All right, so here we have our supply voltage, and I've actually already made a mistake. Typically, for a PMOS device, we're going to call the voltage at the top VSS because it's the source that's at the highest potential instead of VDD. Okay. Yep, literally doesn't matter. It's just a supply voltage at the top of the circuit. Just call it 5 volts if you don't want to give it a name, whatever. Here's our resistor R1. Over here we have VSS. Here's our resistor RS. Here's R2. Here's our resistor RD. And then our drain current is flowing down through the device exactly like we had it. Current is flowing from high potential to low potential in both cases. Our gate source voltage now looks like our source gate voltage here. And then this is our source drain voltage that we are interested in. I'm not going to bother writing down the parameters for saturation and triode and all that kind of stuff again, because we literally just wrote them down a couple of minutes ago. We're just going to apply them directly to this thing, right? So to analyze this circuit, we're going to do pretty much exactly what we did on Wednesday. We're going to assume that the device is operating in saturation and then hope we're right so that we don't wind up having to set up a system of equations. But if we do, I'll help you set up said system of equations. All right, so by inspection, let me put this here. So this is the voltage at our gate with respect to ground. By inspection, this voltage is still just the voltage given to us by our voltage divider. So this is going to be VSS times R2 over R1 plus R2. Let me. All I'm doing right here is I'm scooching that positive polarity terminal down underneath the resistor so that it's very obvious there's a voltage drop across the resistor. There's a voltage drop from here to here. The SG, and then there's the voltage drop. So it technically have some voltage. Oh, and then plus VG. Yeah, sorry, brain fart. So we can say that VSS is equal to ID times RS plus our voltage VSG plus our voltage VG, and rearranging, we're going to have ID is equal to VSS minus VSG minus VG divided by RS. And now I'm going to expand this out a little bit. So VSS is going to be by itself. VSG is going to be by itself. But VG can be expressed in terms of VSS, right? So this will be VSS times R2 over R1 plus R2. And then all of this is multiplied by 1 over RS. And then going one step further, we can see that we have VSS times 1 minus R2 over R1 plus R2 minus VSG. And as it turns out, 1 minus R2 over R1 plus R2 is the same thing as just R1 over R1 plus R2. So we can get rid of something there. So there is a relationship for our drain current. Okay? We can set this relationship equal to our saturation mode drain current when we're assuming saturation mode, or we'll wind up setting it equal to our triode mode current when we're working out things in triode mode. So just laying the groundwork here. Okay. So these are our general relationships. So for saturation, without channel length modulation, we have VSS times R1 over R1 plus R2 minus VSG all times 1 over RS is equal to 1/2 KP times VSG minus the absolute value of VTHP quantity squared. Algebraically manipulating this expression winds up giving us 1/2 KP RS VSG squared plus 1 minus KP RS times the absolute value of VTHP times VSG plus 1/2 times KP RS times the absolute value of VTHP squared minus VSS times R1 over R1 plus R2 is equal to 0. We once again have a big quadratic equation that we can solve just using our quadratic formula. And as per usual, we're going to wind up throwing away one of the solutions of this, one of our VSG solutions, because it's actually not going to have the device in the correct mode. Right? So our correct solution for VSG is going to be VTH minus 1 over KPRS plus the square root of 1 over KPRS quantity squared plus 2 over KPRS times VSS, R1 over R1 plus R2 minus the absolute value of VTH. Once we know what VSG is, then we can directly solve for our drain current ID using either this relationship up here or this relationship over here to the right. And then we're able to solve for our source drain voltage, right? So our source drain voltage, we can figure out what's going on. So we would have VSS is equal to ID times RS plus RD plus VSD, and we're just going to rearrange. So KVL down the right-hand side tells us that VSD will be given by VDD minus RS plus RD times ID. So that's what our relationship looks like for saturation without channel length modulation. Now underneath here, I'm going to do for saturation with channel length modulation, and then I'll finally do triode. Mr. Tamburo. Yep. Thank you for that. All right. So for saturation with channel length modulation effects included, we're effectively just going to use this relationship right here, but tack on a 1 plus lambda VSD, and that takes care of one relationship. And then our source drain relationship is going to be something similar, right? So VSG is VSS minus IDRS minus VG, which looks like VSS times R1 over R1 plus R2 minus 1/2 KP RS VSG minus the absolute value of VTHP squared 1 plus lambda VSD. VSD is VDD minus RS plus RD times ID. Keep saying VDD even though it's supposed to be VSS. So this is going to look like VSS minus 1/2 KP RS plus RD VSG minus the absolute value of VTHP quantity squared 1 plus lambda VSD. And we now have our 2-equation, 2-unknown system that we can throw into our computer to solve for VSG and VSD. And then we just plug those values into our equation for our drain current to get that part of the operating current. So all of saturation is effectively covered. Now let's talk about driver. So for triode mode operation, once again, VSG is equal to VSS minus IDRS minus VG. Substituting in our relationships for VG and ID, this becomes VSS times R1 over R1 plus R2 minus KP RS VSG minus the absolute value of VTHP times VSD minus 1/2 VSD squared. And then VSD, once again, is VDD minus RS plus RD times ID. Damn it. VSS goes there. VSS minus KP RS plus RD VSG minus the absolute value of VTHP VSD minus 1/2 VSD squared. 2-equation, 2-unknown system. Solve it, plug the numbers in to solve for ID. So those are all of the relationships that you could ever possibly need for a PMOS transistor in a 4-resistor bias network. So now we'll look at our self-biasing networks. Here's our supply voltage VSS, RS, RG, and RD. This is our voltage VSG. This is our drain current ID. This is our voltage VSD. We know that there's no current flowing into the gate terminal of the device, which means the current flowing through RS is also ID, and all of the current flows out the drain of the device. So all of ID is flowing through RD as well, right? Okay, so I'm staring at this because I'm trying to actually make sure whether or not this resistor isn't supposed to be connected down here. Because for this particular configuration, VSG and VSD are supposed to be literally the exact same things. So that would require our gate to be at the same potential as our drain, which means I think this resistor is actually supposed to be connected down here at our drain terminal because it's at the lower potential. So I drew it like it was the NMOS instead of the PMOS. So let me fix that really quickly. Glad I was paying enough attention to notice that. Yep, there we go. None of those voltages or currents are literally going to change at all, right? This is still the potential difference between our source node and our gate node. This is still the potential difference between our source node and our drain node. But now we can see that our gate and our drain are at the same potential, right? So that VSG and VSD are the same thing. So sorry for that mistake. So since VSG is equal to VSD, our device is always in saturation. So let's see here. Doing KVL around the right-hand path, we would have VSS is equal to IDRS plus VSG or VSD because it's the same thing, plus ID times RD. Rearranging this, we have ID is equal to VSS minus VSG divided by RS plus RD. And so now we're going to set this equal to our drain current relationship for saturation mode region. So without channel length modulation, we have VSS minus VSG divided by RS plus RD is equal to 1/2 KP VSG minus VTH quantity squared. And once again, we're going to wind up having a quadratic function. So rearranging this guy is going to give us 1/2 KP times RS plus RD times VSG squared plus 1 minus KP RS plus RD times the absolute value of VTHP, all of that times VSG plus 1/2 KP RS plus RD, absolute value of VTHP squared minus VSS, ran out of room there, is equal to 0. That's going to have two solutions, only one of which will work out to be in the right operational mode. So the solution that we keep is VHD is equal to absolute value of VTHP minus 1 over KP RS plus RD plus the square root of 1 over KP RS plus RD quantity squared plus twice VDD minus the absolute value ESS, excuse me, minus the absolute value of VTHP divided by KP RS plus RD. And then lastly, with channel length modulation included, we find that VSG is going to be equal to VSS minus 1/2 KP RS plus RD VSG minus VTHP squared times 1 plus lambda VSG. And we get a third order polynomial in VSG that we can use our computer or possibly our calculator. Some of our calculators have a third order polynomial folder. I think the TI-36 is good. I'm positive the Casios do, or whatever it's worth. So those are our relationships. So PMOS done. Aaron. So our constraint is that, let me put it down here in blue, right? So we want VSD to be greater than VSG minus VTHP, right? So VSD is equal to VSG means that VSD is always greater than VSG minus some number. So it's always in saturation. So this is our constraint for saturation, and then we're simply observing that this number will always be greater than this exact same thing minus a positive number. We're done. All right, so on Monday's class meeting, we're going to start looking at amplifier circuits formally and all that kind of good stuff. We're going to spend the overwhelming majority of our time looking at how BJT-based amplifiers work. We have not yet covered the small signal model for MOSFET, so we'll probably wind up doing that probably on Monday of next week, definitely by Friday of next week. And what we're going to see is that effectively the small signal model of a MOSFET and the small signal model of a BJT are literally the exact same circuit except for one small change. And the BJT model is a little bit harder, so we're going to use that one, and then we can effectively just take the limit of what the BJT response is under a certain parameter to figure out how all the MOSFET stuff works. So if we can understand how a BJT amplifier works, we already know how the MOSFET works because the small signal models are effectively identical. All right. Have fun eating lunch or whatever. Yes.
How do CMOS logic?
What do you mean how do CMOS logic gates work?
They're all non. Like, how do they work?
So I'm just trying to remember if the PMOS is supposed to go on top or bottom of an inverter. I think it goes on top, yeah. Yep. So that's our basic inverter, right? So let's label some voltages here. So this, let's call this transistor M1. So this will be VGS1. This is transistor M2. So this will be VSG2, right? And just to recall things, this is not part of this class, by the way. You don't have to pay attention to this. I'm just trying to answer a question. So for NMOS, we know that VGS needs to be greater than or equal to VTH for not cutoff mode. And for PMOS, we know that VSG needs to be greater than or equal to VTHP for not cutoff mode, right? Okay, so let's say that I put high voltage here. If I put a high voltage here, then this transistor M1 is not in cutoff mode. But this transistor is. Because there's no current flowing through this transistor, then let me think about this. And there is a conducting path through this transistor, it's going to pull the output low. So when our input is high, our output goes low. So that's an inverter. Yep. And then in the opposite case, if we put our output, or excuse me, our input as low, this guy turns off, this guy turns on, so that pulls our output high. This is literally just a simple.
But it's just getting the digital design pass like 2 days ago. And I was like, I don't know how that works. Okay.
I can't remember what the inside of an AND gate and an OR gate and all that kind of stuff look like off the top of my head, but it's a similar type thing. Yeah.
No, I don't. It's like, it's just like a volume, it's like a knob, but for current. I don't know. The more you increase the current, the less you have. Discord last night and saying but like, I'm not wrong though. You're not. Short RP. Yeah. According to. Your calculation problems and all that kind of stuff. It's like. Oh, and it's a different line. So your question would be, how does it work? How does the loss? Now, articles are required to see all the parts of the equation that are just. Yeah. There's so many things.
So the channel being there or not being there is whether or not we are in cutoff or not cutoff, right? So if the channel isn't there because we don't have strong inversion, we are in cutoff mode. If the channel is there because we have strong inversion, meaning our gate source voltage is greater than our threshold voltage, then the channel is there. So looking at an NMOS, we know that our drain current ID in saturation is 1/2 Kn times VGS minus VTHN squared. This Kn term is mu n C ox W over L. So if L gets smaller, Kn gets larger, our drain current gets larger. That's literally it. So let's visualize it. So here, let's do VDS is equal to VGS minus VTH, right? So that would look something like this. So our charge distribution in our channel is linearly changing from the source side to the drain side, and our pinch off point occurs at exactly the full length of our channel, right? For VDS greater than VGS minus VTH, now that pinch off point is going to occur further in. So here is where L was. This is our new effective length. And because that L effective is smaller, how does the current flow? Okay, so let's think about things here. Okay, so these are NMOS transistors. So we have a, let's see. So if we assume that our source is at ground, just for the sake of argument, and our body is at ground as well, we have an unbiased PN junction right here. On this side, we have a high voltage applied here, and then a low voltage here. So this is an N implant. So we have a reversed biased junction. Okay. So effectively, we have a reverse bias junction. So we're going to have a large field that's going to try to sweep carriers across this little gap. Yep.
So channeling quantum emitters that how that changing.
Yep. How much the effective length of the channel is changing due to our applied voltage. That is literally all channel length modulation is. Much like in a BJT, the early effect is just taking into account the fact that the width of the depletion, or excuse me, the width of the base region gets smaller when the depletion region of the base collector junction gets larger. So we are changing the length across which our charge carriers travel. For a BJT, that means that there's less chance of recombination occurring, which results in a higher current flow. Yeah. So similar results from wildly different physics, which is all how BJTs and MOSFETs, like they do the same job. They just do it differently. Once we get the small signal, it's all the same. Yep. Although, yeah,